Thanks everyone for coming. So one remarkable ability of human visual system is that we're able to perform single image 3D inference tasks from a single 2D image. For instance, from this single image, we are able to infer that the biker is closer to the camera than the building and the minivan in the background. The road is flat and its distance to the camera varies smoothly extending to the horizon. We can also infer that the surface normals from a single image, like knowing in this case the floor tiles are facing up, and the fridge is facing towards the camera, and the cabinet is facing perpendicular to the ground. Or we can even do mental rotation of associating images of objects located in different degrees. Actually, why don't we do a test here? One of the two images on the right is a rotated version of the image on the left. So how many of you think it's image A, like the first right image? How many of you think it's right? I guess the rest? OK, I think the majority of us got it right. So it's the first image. So we're pretty good. What's remarkable is that all these tasks are mathematically under constraint to solve from a single image, since the projection has killed all the information about the third dimension when you form a single 2D image. In fact, a single 2D projection could be produced by any of an infinite number of 3D geometrical configurations. For instance, an image on the top could be a picture of a piece of folded paper standing on a table. Or it could simply be from a 2D painting. It could also be a picture of a very complicated sculpture. So how is it that we are able to make 3D inference from a single image in most scenarios, given that it's mathematically under constraint? One hypothesis is that this is possible only because our world is structured and exhibits consistent regularities. If our world were an abstract world with pieces of matter floating in the mid-air, we would have no chance of getting a 3D geometry from a single image. Fortunately, since our world is structured, the ground tends to be flat, the buildings tend to be straight, and objects like cars and pedestrians always have regular shapes. And by moving around and exploring the 3D space, we are able to observe millions and billions of 2D projections of the 3D world. And from these 2D projections, we have learned an internal model of the 3D world that consistently explains the observations. Notice that this is very different from how the classical structure from motion work approaches the problem, where the goal is limited to reconstructing the 3D model of a single instance. And because there's no learning, the data you used for reconstructing an instance does not help you in any way for reconstructing a different instance. And furthermore, such approaches have to rely on using multiple views for optimization and are incapable of single-view 3D inference. So in this talk, I will present two of my attempts in mimicking the setup of human visual learning to train systems that do single-image 3D inference from observing only 2D views during training. The first task we consider is view synthesis. Given a single 2D image, the goal of this task is to synthesize new images of the same object seen from different camera angles. One can see this as a computational equivalent of mental rotation, like we showed in the first slide. Since the success of deep learning, there has been several attempts in doing this task from a learning perspective. All these methods share a similar pixel-in, pixel-out pipeline, where they train a CNN that directly regresses from the input view to the desired output view and uses the L2 pixel reconstruction loss for training. As a result, the output of their method tends to be blurry and in low resolution, with most of the texture details missing. This is because when training with the L2 loss, the network is perfectly happy to predict a mean image that is in between different modes of the distribution. So to deal with this, we propose a simple but effective method based on the insight that the pixels are highly correlated between different views of the same object. For instance, given a left view of a car, we can simply mirror all the pixels to get a right view without needing to see any pixel from the right view. Therefore, we can learn to synthesize the novel view by simply copying the pixels from the input view. And we call such flow field appearance flow, since its pure objective is to reconstruct the appearance of a different image. Notice that here we are still using the same L2 loss as before, but with the constraint of forcing the network to only use pixels existing in an input image, in the input view. So why does it avoid the problem of collapsing to the mean? Because now the network can no longer hallucinate mean pixels and have to work with pixels that exist in the input image where no mean pixels exist. Another nice property is that by predicting the flow as the intermediate output, we could easily interpret what the CNN is learning. Here's an illustration of our network architecture. Given an input view and a viewpoint transformation, we run through an encoder-decoder network that outputs a per pixel 2D flow field that indicates for each pixel in the target view where to sample the pixel in the input view to reconstruct itself. The process could be implemented in a differentiable manner using the spatial transformer network. As it turns out, such a simple trick leads to much better results than the direct pixel regression. For instance, in the first example on the top, the texture details on the car body has gone completely missing in the pixel regression output, while they're still preserved in our results. Here are some more results on the ShapeNet dataset. As some of you might notice, the network sometimes struggles in predicting the views that are not highly correlated with the input view. For example, when synthesizing the back view from the frontal or the side view, you see some noticeable artifacts. This issue has been recently addressed in a follow-up work from UNC that will appear in CVPR 2017, where they combine the benefits of flow-based synthesis with another disacclusion implanting network dedicated to hallucinating regions where flow-based solutions struggle. This has led to some improvement of our appearance flow work. Now let's take a step back and look at the pipeline from a higher level. So in direct pixel regression, it's a pixel-in, pixel-out pipeline with CNN acting as the black box mapping between the input and the output. In our appearance flow work, the CNN instead needs to learn to associate pixels between the input and the output. And notice that such pixel associations naturally emerge as the result of learning view synthesis, and we do not provide any ground truth supervision for the flows. So the emergence of flow fields from learning to synthesize a new image is an example of the old school analysis by synthesis paradigm. And led me to wonder, can we go even further and distill more factorized geometric output than the flow field? So in this second project, we are particularly motivated by the setup of unsupervised learning from videos, where we will want an agent, in this case a car with a monocular camera, to move around and explore the world while capturing the video for training. By observing many different parts of the world, the agent should learn about the regularity of the 3D world and be able to apply their knowledge to a new scene when doing inference at test time. More specifically, from a large set of unlabeled video clips, our goal is to train both a single view depth CNN that infers per pixel depth from a single input image and a post CNN that infers the relative camera transformation between a set of input views. While the depth and the post CNNs are trained jointly at training time, they can be applied independently at test time. Our approach takes inspiration from the recent success in learning depth from posed image sets. One such representative work is deep stereo, where the basic setup is that given two input views from left and right, you want to train a CNN to synthesize the central view. To do so, they use a plane sweep volume representation and project the input views onto a set of quantized depth planes like 3 meters, 5 meters, 10 meters from the camera, and ask the CNN to predict the correct depth that could successfully reconstruct the central view based on simple projection. While deep stereo works great for view synthesis, the depth it produces is coarse and quantized due to the plane sweep volume representation. Also, it requires multiple register views at test time. So potentially, you could just run a multi-view stereo matching algorithm to get a depth map. Then in ECCV last year, Garg et al. Proposed a method that removes the need for the coarse and expensive plane sweep volume representation and learns a single view depth CNN using images taken by a stereo camera during training. The supervision signal, again, comes from the reconstruction error of projecting the right image to the left image based on the predicted depth or disparity. One issue with deep stereo and Garg et al. Is that they both require multiple calibrated cameras during training, which is not realistic in many scenarios where only monocular video streams are available. So in this work, we extend their approach to handle the scenario of only having access to videos taken from a monocular camera. Our approach is similarly based on the idea of using a meta task of depth-based view synthesis as supervision. Recall that in order to perform depth-based view synthesis, we need two sets of quantities. One, the per pixel depth from the target view, and two, the relative camera pose between the target view and the source view. So given the depth and the camera pose, one could then synthesize the target view by using pixels from the source view by projection. In other words, if we could use CNNs for estimating the depth and the pose, and formulate the entire pipeline in a differentiable manner, then we could use view synthesis as the meta task for training the depth and pose CNNs jointly without any supervision. So here's an illustration of our training pipeline. Given several consecutive frames from a video, we train the depth CNN to output a per pixel depth for the central frame, and the pose CNN that outputs the relative transformation between the central and nearby cameras. So given the depth and the camera pose, we can then project each pixel in the target view to the source view, and measure the reconstruction error as the loss function. So in this paper, we use L1 pixel error as the metric. Alternatively, one could use other metrics like CNN feature reconstruction or SIF feature matching errors that are potentially more robust to lighting changes. Any questions so far? Okay. So when doing the projection, we again use the bilinear sampling mechanism from the spatial transformer networks to allow the entire procedure to be differentiable. More specifically, given a pixel from the central view IT, we first project it onto the coordinate frame of IS based on the predicted depth and the camera pose. And then we do linear interpolation around the neighborhood to obtain its reconstructed pixel value. One issue with this type of training is that the gradient signals tend to be very local, since the error is only dependent on the immediate neighbors of the projected coordinates. So in this case, the gradients can only be derived from the pixel error difference around the neighborhood. So to combat this, we use a multi-scale prediction mechanism such that the gradients can be derived from a larger region in higher scales and gradually propagated to lower scales. One remaining issue for applying the above learning framework to monocular videos is that it does not model the dynamic objects and occlusion. So the gradients will be corrupted if these factors occur during a training sequence. To deal with this, we simultaneously train a network that outputs the network's belief in whether each pixel in a target view could be successfully expanded by the view synthesis model, which is used for regularizing the loss during training. Empirically, we have found that the expandability regularization slightly improves the final result, but it's not critical to the success of the overall training pipeline. So in this case, maybe I'll show the network architecture here. So in this case, we have two sets of network. The first network basically outputs the single view depth, like in multiple scales. And the second network outputs the camera pose between the target view and the source views. And then there's expandability mask that sort of indicates for each pixel whether it can be successfully reconstructed using the predicted depth and the camera pose. So a trivial solution would be to just predicting everything as unexpandable, then the loss will be 0, probably minimized. So basically, we need to add a regularization term to encourage it to expand as much as possible, but allow it to allow some slack for it so that when dynamic objects and occlusion occur, they don't need to derive gradients from those regions. So we apply our learning framework to Kitty and the cityscapes. So those are sort of data sets of car driving in urban scenes. And notice that while these two data sets include stereo images and the car odometry measurements, we do not use this information and only use a monocular video stream for training. So here's a sample result video on cityscapes. So this is frame-by-frame prediction without any temporal smoothing. So you will notice some amount of jittering between frames.
Can you show it with a warping detection forward?
Oh, like the projection errors? Yeah, I should show that somewhere.
How should I compare it to classical approaches?
Well, this is single view depth, right? So classical approach would not be able to do it. You have to do learning.
Okay, but even there actually, okay, one classical thing would be just the ground plane. The ground plane constraint that you can do classically.
Oh, okay. Right, but then you wouldn't be able to get the other objects, right? Like the cars, buildings, pedestrians, trees.
No, I think the point here is that this kind of jet color map of depth is traditionally hard to read and.
This is actually not jet. This is more recent, perceptually acceptable color map.
Yeah, but still, people don't know
how good is this.
I see.
I think they know how good is this.
Like if you take the image, warp it using this depth,
Oh,
and
I see.
display it as a kind of a graphics thing. Then
Right.
you know.
Okay. Okay.
Okay, but then
But I want to see it in a couple of different ways. I mean, there's nothing metric here, right? And I'm thinking, for example, that the boundaries are probably not good.
No, it's
The
not.
object boundaries are pretty bad.
Right. Mm-hmm.
So when I want to see that, I mean, when I just see a video, the pseudo kind of.
Looks like you could go without bumping into stuff, maybe.
So the affordance, yeah.
Okay, just to show another video.
But like, it seems just too blurred to me. I mean, like, would I trust this for detecting pedestrians? I mean,
probably not. You shouldn't. This is unsupervised. Yes.
So, PD has like that ground truth, so we can
Right.
provide numerical value. Why not?
You mean?
Quantification of your error.
Oh yeah, yes, we have numbers. So we're actually slightly better than the eigen method, which uses ground truth depth for training.
Sure, but I'm saying that what you're showing in the bottom can be actually your error heat map. You can.
Oh, well, the problem is that the KD ground truth is sparse. It only has, like sparse points on the for each depth map.
That's enough to make at least a regional with some bilinear interpolation.
Okay, yeah, I could try to include that.
I mean, it's not perfect because maybe your absolute depth is off, but if the relative depth is correct, so that might actually overstate theirs.
Right. So
it's more like this plane-based, like can you get the right planes? It's really the obvious application of this. Yeah, can you get the ground plane? Can you get the planes of the pedestrians and the buildings, something like this? Like maybe thinking about what do you want to use it for, and then visualize it in that context.
Yeah, that's a good point. Yeah, so for benchmarking, since there's no other work that learns single view depth from molecular videos, we compare with some of the supervised baselines. So the second row is the prediction made by a deep learning method that uses ground truth depth for training. And the third row is the output by Garg et al., so the one I talked about earlier, which uses stereo cameras for training. You can see that our unsupervised prediction is comparable to this.
Yeah, this is fine. Yeah. But in a way, I mean, the term unsupervised is a little strange here, right? Because it is supervised by the SFM signal, basically.
But you don't have any supervision for the pose or the depth, right? So it's basically like observing videos, and then you.
But since
Was it supervised by hardware on the Kinect, or was it supervised by software?
Long before the term, before supervised learning took over this field, we knew about structure from motion, and we knew that from multiple views in a moving camera, it has the signal from which depth can be calculated. And that depth can be calculated, and obviously the signal there is that you have a putative movement, and you use that to predict what the view would be. Right? And then you have a loss function. I mean, these used to be called direct methods.
Right, yes.
A paper by Pond and Nagader for 1987 or something like that, right?
Yes.
So it is that signal, right, that you are exploiting.
Right, so you're using geometry, so the projected geometry as the supervision.
Yeah, so the signal is really the one which you would be there in your classical structure from motion. And that provides a depth which then gives the supervision.
Yeah.
I mean, Kinect, which is what the other guys train on, is also basically using the same signal, right? But it's in hardware.
Right. So let's see. So I guess like all the.
Kinect is not supervised, right?
But the same token, yeah. The same.
You could say, Kinect could certainly be advertised as unsupervised.
So I think here I just want to make the point that there's no access to any ground truth depth or ground truth pose. So it's like using some kind of meta task for learning these two intermediate tasks.
Meta task being computer vision.
Yes.
I'm being a bit pushy, but because now this has become pretty common, and I think actually it's a perfectly reasonable thing to do, to bring in traditional the constraints from traditional computer vision.
Right.
Okay, but what I don't like is the fact that to market it to the heathen of today, you have to advertise it as unsupervised. And that's what makes it appealing, the fact that it is unsupervised.
Right.
Well, I think what you can say is, directly from the pixels. right? Because Kinect, there's active elimination, there is this, and there is that, or, well, I guess it's, what are they using? How do they get ground truth here in outdoor?
Laser scanner.
Laser, yeah. So there's no laser, there's no.
But they were classically these optimization approaches where, I mean, this is what Horn always argued for. In fact, those were the earlier methods. Then it moved, so in the 80s, there were approaches which tried to, these were called direct methods.
Right,
Verdon and Horn and Nagarkar and so on. Then in the 90s, I remember being in a debate between direct methods versus people who said you should use a small number of feature points at which you can get good correspondences. So this used to be the debate at that time.
I think here the argument is, because a lot of people now just say, okay, when you need to solve a problem, label things and you're done. And I think Tinghui is arguing that, you know, this is, you don't need to just go and label things, right? That you can get stuff from the signal itself. And I think in that sense, it's one version of the word unsupervised, although it's
no, I agree with that. I'm just quibbling about the fact that this conversation we are having, because it's 2017.
Right.
If this was 2011, you would do this but not call it unsupervised.
No, because here they're still learning, right? They're still, at test time, it's still a single image.
Yeah.
So, yes, you're using the classic methods for training, but at test time, it's still very much, you know, post-2012.
Yes.
Okay. Well, didn't you have a paper in 2007 with Derek Hoyle?
Yeah, this is way better.
Yeah, okay.
Okay, yeah, you should compare with like the old style, like the Saxena and the Derek things.
Mm-hmm. The photo pop-up, or which one?
Yeah, photo pop-up, the Saxena kind of depth.
Make 3D.
Make 3D.
Oh, Make 3D.
Because those are really the competitors, yeah.
I think their numbers
But they're actually also supervised. And Derek was clicking on super pixels, you know, for like days. So
yeah.
Anyway, continue.
Yeah, we were worried about getting into this kind of argument if we use like multiple views. So yeah, we basically remove any sort of multi-view depth experiment in the final paper. Just have single view. So you have to do learning. So you can't just do classical methods. But yeah, but I agree the unsupervised learning term is kind of, you know, not very, very, very appropriate here.
We're actually almost out of time, so
Oh, okay, yes. All right. So a typical failure case of our depth prediction model occurs in sort of vast open scenes. In these scenes, since most of the objects are either far away or have uniform textures, so the gradients you derive from pixel reconstruction are not very meaningful. I'll just go through some other things. So to test the cross-dataset generalization ability of our model trained on kitty and cityscapes, also just apply it directly to the Make 3D dataset without seeing any Make 3D image during training. The results are not great in the fine details, but still reasonable in getting the global scene layout correctly. So we also evaluated the performance of our pose estimation network on the kitty odometry dataset. We compare with an award-winning SLAM system called OrbSLAM. Specifically, we compare with two variants of OrbSLAM. One using 5-frame snippets as input, so this is the same as our input setting. And the other using a full driving sequence of like about 1,000 frames to allow loop closure and relocalization. So this variant uses strictly more data than our model. Here I'm showing the error plot with respect to the amount of turning magnitude from the beginning to the end of an input sequence. So as it turns out, we are consistently better than, okay, so this is OrbSLAM short. So this is ours. So we're consistently better than the OrbSLAM short across the entire spectrum, especially when the turning magnitude is small, so the car is mostly driving forward. And then we're also comparable with OrbSLAM full, which uses strictly more data during training, using more data for estimation. Yes?
in the
So basically, when calculating the error, we basically normalize. We do a scale optimization for every method, so they are aligned with the ground truth scale. Okay, last slide. While the results seem promising, there remain some limitations and challenges we would like to address, hopefully in the near future. First, we would like to be able to explicitly estimate the scene dynamics and occlusion. Both are important for 3D scene understanding. Second, we would like to be able to remove the need for camera intrinsics, maybe include that as part of the estimation process. So this is required if we want to train a system on internet videos. And third, we would like to have richer 3D scene representation than a depth map like layers or voxels. In fact, one of my co-authors, Shubham, who's a big fan of full 3D prediction, has done very cool work in learning volumetric predictions from 2D supervisions. So definitely check out this paper if you are interested in this direction. I'm also an author on the paper, so it's kind of shameless plug. Okay, thank you. Thank you for your attention.